I'm Matthew Abraham. For my Capstone project, I implemented a compiler for a custom statically typed programming language, which I called MattyLang. To get started, let's look at some example code. MattyLang has common procedural constructs such as conditional statements, loops, and functions. We can run this code using the command line interface. And we can see that it successfully executed and we got the results we expected. Fibonacci of 5 is 8. Apply if add both positive 5, 10 is 15, negative 5 and 10 is 0. The implementation process follows an agile approach. So the language was split into 3 versions. Version 0.1, which implements the base of the compiler with support for variables and expressions. Version 0.2, which implements control flow statements such as if, while, continue, and break. And version 0.3, which implements functions, function types, function calls, and the return statement. One major focus is to ensure the code base is readable and accessible. As such, the compiler was written in Python 3. Furthermore, the compiler does not actually have a runtime. MattyLang compiles into Python, which is then executed. So when we ran this here, this actually generated what the output of the compiler was, which is Python. And we can see this is actually being executed to print this. So if we run this Python, we'll get the exact same result. The compiler is split up into 5 main components. There's the lexer, which performs lexical analysis. Specifically, it tokenizes the input for the parser. Then the parser, which performs syntax analysis. This generates the undecorated abstract syntax tree, which merely represents the logical structure of a program. Then we have the binder, which is a visitor, and this performs the first part of semantic analysis. Specifically, it performs name resolution. It generates a symbol table and binds symbols to identifiers. Then we have the checker visitor, which performs the last part of semantic analysis. It performs type checking, type inference, and it also binds types to expressions. Finally, we have the emitter, which is also a visitor and performs code generation. So the emitter takes in the decorated abstract syntax tree. There should be no errors when it's invoked, and it'll generate the Python code. So we can see roughly the process here. The lexer is fed into the parser, then an undecorated abstract syntax tree is met, then then semantic analysis occurs here in 2 stages. So we have name resolution, and then we have type checking. And then finally, after all of that happens, the code is emitted. As with many other compilers, the MattyLang compiler attempts to continue parsing even when a compilation error occurs. This allows the user to check the entire program with one invocation of the compiler. So we can see an example of this by running MattyLang in repel mode. So if we have a type error, let's say we have 2 type errors back to back, we'll get those 2 errors. It won't stop parsing. One of the most complex features was implementing return type inference, as every chunk within a function must properly be checked to ensure they all return the same type. So we can see this in the checker. So once we visit for every return statement we visit, we can see that we get an enclosing chunk here. Check if it's assignable to the previous type if it's been specified, and if it's not, we emit an incompatible return type diagnostic. So if we run this here, so if we go def if true, return 1. So we have incompatible return types. So we have incompatible return type string expected real, because the first return type found returned a real. This is very important as it lets programmers find all of the errors at once. The testing process is driven primarily by code coverage, with more than 95% of the code base currently covered by the test cases. So we can generate this report by first running the test suite using the coverage Python module, using this command, which can be found in the README as well. And then we got no errors, and then we can generate a coverage report by using this command. And then we can see we actually have 96% code coverage. And this includes all of the most important parts of the compilers, such as the parser at 100%, the lexer at 100%, the visitors at nearly 100%. Another unexpected feature that had to be implemented was variable renaming during code generation. Because Python is not block scope, but rather is function scope, variables in MattyLang that conflict with a variable in an outer scope must be renamed to ensure that the generated Python code remains valid. So we can see this if we turn on verbose mode, as well as we show the code generated. We have two variables with the same name in within the same parent scope. In Python, this actually is one variable, and this one would just reassign to this variable. But in MattyLang, since there is proper block scoping, these refer to two separate variables. So when we generate this code, we see that the variable, one of the variables named x was renamed to x1. So we have x is 1.0, x1 is 2.0, and then the prints are properly adjusted. The references to them are also properly adjusted. In the future, I'd like to expand MattyLang to introduce a lot more features. Module imports and exports are a big one. I think this will be the first big feature I implement after the capstone. Compound types and tuples. Runtime, so I don't have to emit Python. A standard library. Closures and lambdas, integers, arrays, and so forth. Thank you for listening to my presentation.